Hello everybody. In the last session we had quite some detailed discussion on the transfer functions in the pole 0 domain, modeling of circuit in the pole 0 domain. We saw that the transfer function is a special case of the state equation where the initial conditions are 0, and then we towards the end of the last session we also saw that there is a procedure, a method to extract the transfer function from the state equation. Basically the transfer function is C S I minus A whole inverse into B plus D, that is using the A, B, C, D matrices as the input matrices you can obtain the transfer function. We will see some of those examples in MATLAB today. Further, today we will try to consolidate the concept of pole 0 in the pole 0 domain using the transfer function model. We shall start by the simple circuit, which is the RC circuit, and then take up the RL circuit followed by the RLC circuit. So, this RC circuit, by now you are all familiar with this particular circuit and its state equation and also its transfer function equivalence. Now, this has a VI source voltage, there is a resistance R, there is a capacitance C which has a voltage here Vc, which is the state variable in this case because C is the energy storage element. Now, this let us shift or represent it in the Laplace domain or the S domain or even the pole 0 domain as we have been calling it. So, in the Laplace domain we still have the same topology of the circuit. We have the R, we have the C, now here the variables are represented slightly differently. Lower cases are made upper cases. Now, they are functions of S. Vi is a function of S, Vc is also a function of S, and Vr will also be a function of S. R is the parameter and the capacitive reactance in the S domain is given by 1 by Sc. This we saw in the last class, that we just need to replace j omega terms in the reactance, that is j omega with S. So, which means 1 by j omega C becomes Sc, the capacitive reactance in the Laplace domain, and j omega L becomes Sl in the Laplace domain. So, now this circuit, that is this circuit which we have transformed to the Laplace domain, let us obtain a transfer function. And we know that we also have seen that obtaining the output transfer function by the input, obtaining the transfer function of the output by the input, Laplace transform of the output by the input as it is defined, is just like in any resistive network. In this case it is the capacitive reactance 1 by Sc divided by R plus 1 by Sc, and this can be written as 1 divided by Src plus 1, or still further simplifying it, you have 1 by Rc divided by S plus 1 by Rc. This is one transfer function that we have obtained for the circuit wherein the transfer function is basically in this case defined as the Laplace transform of the output variable V c divided by the Laplace transform of the input variable V I. But one need not look at the transfer function just as the output variable V c by the input variable V I. It could be any variable, it could be the branch currents, or it could be voltage across any other component in the circuit, in the same circuit. So, if you take the same circuit, let us say we would like to see the voltage across V r. What is the transfer function of the voltage across V r with respect to the input V I? So, if we look at that, let me just have a copy of this circuit. In our next page. So, we saw that we had VCS by VIS equals 1 by RC by S plus 1 by RC. Here the numerator does not contain the S terms, which means there are no zeros. The denominator contains one order of S, that is S to the power of 1. So, there is only one pole, and that pole is at S is equal to minus 1 by RC. This we saw the last class. Now, what will you get if you want a transfer function of VRS by VIS? You would like to have a transfer function of the voltage across R with respect to the input voltage. Now, here the voltage across R divided by R plus 1 by SC. So, this would be the ratio in which they divide the resistance divided by the resistance plus the capacitive reactance. So, this on simplification would give SRC divided by SRC plus 1. Slight further simplification will give you S divided by S plus 1 by RC. You see, this is a bit slightly interesting result. Here you have a numerator polynomial S, which is of the order of 1, which means there is a 0 at S equals 0. There is of course a pole at S equals minus 1 by RC. So, you see, for the same circuit I can have different transfer functions depending upon what is the output variable that I want to choose and what is the input variable that I want to choose. Now, these two transfer functions for this circuit, that is VCS by VIS, which is equal to 1 by RC by S plus 1 by RC, and VRS by VIS, which is equal to S by S plus 1 by RC. These are the two transfer functions that we just obtained. This output variable VC across the capacitance with respect to the input, the voltage across the resistance with respect to the input. Now, here if you see, the poles are the same, they have the same pole locations, only in this case there is no 0, there is a 0 here in this case, a 0 at S is equal to 0. How do they affect the responses. We will shortly have a look at it in the MATLAB. Now, we could also get the same transfer function by, as I said in the last class, by the process of converting the state equation to the transfer function form using the conversion matrices or the conversion process that we discussed in the last session. So, for this particular circuit, we also saw that the state equation for this circuit, we already know, we have done this many times, but still for the sake of clarity I will just quickly write that down. Vc is the state variable, so dVc by dt is equal to minus 1 by Rc, which is the A matrix, into Vc plus 1 by Rc, the B matrix, into Vi. This is the dynamic part of the state equation, and of course, the output equation we saw Vc equals 1 Vc plus 0 Vi. Okay, this is the output equation. Now, we shall do a small process, that is, we take this state equation model, input it to MATLAB, so in MATLAB let us make a conversion state space to transfer function model and obtain these models depending upon what we want to give as the output variable that we want to see. If it is Vc, then we would like to get this transfer function, and if it is Vr, then we would like to get this model. Okay. So, there are few functions in MATLAB which we can use to do these conversions. I will just briefly describe to you about these things. So, first we go into the MATLAB domain. So, in the MATLAB domain, let us open an edit window. So, we have the edit window here. Let us first give the parameters. There are two parameters. Let us say R1 equals, let us say 10 ohms for now, C1 equals 10 e minus 6 or 10 microfarads. Now, the A matrix is given by minus 1 by R into C. We saw this in the earlier session also. B matrix equals 1 by R into C. Now, if we want to see the output voltage as Vc, then we give the C matrix equals 1 and the D matrix equals 0. Now, this is the model of the RC circuit, which we shall input to MATLAB. Sorry, I will go back to the editor. These are R1, C1, R1, C1. Okay. Now, we copy this, paste, and we have the variables. Now, what do we want to do with these variables? These variables are in the state space form. Now, we want to convert it into the transfer function form. So, we use one function in MATLAB called state space to transfer function form, that is SS to TF. So, this means state space to transfer function form. The syntax is very simple. In fact, in MATLAB it is very friendly. If you want to know the syntax of this, you just have to type help SS to TF. So, you get the syntax of the particular function command. So, what does it say? State space to TF, state space to transfer function conversion. A numerator polynomial, denominator polynomial, this is the output, is equal to the state space to TF, SS to TF function, for which the parameters that you are inputting are A, B, C, D and initial conditions. And for the transfer function which we are trying to calculate, we are going to give initial condition 0. And this will basically use this kind of an algorithm, C Si minus A inverse B plus D. In fact, this is what we derived in the last class, if you remember, of this particular state space form, where A, B, C, D matrices are as defined for a general state equation. So, let us do this particular conversion. Let me have a numerator polynomial n1, a denominator polynomial d1 of the transfer function, which should be obtained after the conversion SS to TF, state space to, and we have the A, B, C, D matrices. So, this A, B, C, D matrices should get converted to the numerator polynomial, denominator polynomial. So, this is the numerator polynomial function of S, this is the denominator polynomial function of S. Of course, it does not look like a transfer function. So, what we can do is, we can represent the system in the transfer function form using this numerator polynomial and denominator polynomial in a more friendly form using the TF function. So, TF, you input the numerator and the denominator polynomials n1 d1. So, that will give you this. So, you see the transfer function now is in our familiar notation. This is 10,000 divided by S plus 10,000. 10,000 is 1 by RC, isn't it? 1 by R was 10 and C was 10 E minus 10 microfarads. So, 1 by RC is going to be 10,000. S plus 1 by RC. Okay. Now, sys 1 is this. What will you get for the pole 0 map of sys 1? You see that in the earlier session when we did the pole 0 map, we had given the state equation as the input, the A, B, C, D. But you have the transfer function model, you can give the transfer function model also. So, sys 1 is the transfer function model. We are given what is the pole 0 map of the transfer function model. So, you see here there is one pole at minus 10,000, which is minus 1 by RC, no zeros. Now, let us try to find out what will be the transfer function for the voltage across R to the voltage that is the input voltage that you are supplying. So, going back here to this portion, I would like to see what would happen to the output equation when you want an output here as VR instead of VC. You see that VR here, this is VR. What is VR? VR is nothing but VI minus VC. So, how does it reflect here? Now, I am going to modify this. I will erase the C's here and I will put that one as R. Now, I want VR. Now, the state of vector of course will remain the same, that is now minus Vc, and therefore, I put a minus 1 here and Vi is a plus 1. So, I erase the 0 and put a plus 1 here. So, this is our output equation now. C is minus 1, D is 1. This is the change that you have to do to obtain Vr. So, let us do that modification in the MATLAB editor. So, we make C as minus 1 and D as plus 1. So, now with this state equation, this represents Vr as the output, which means we can now obtain the transfer function. See, let me clear everything. We can now get the transfer function of Vr by Vis. Okay. Now, we perform the same operation, that is, we now get the numerator polynomial of the second transfer function, denominator polynomial of the second transfer function equals state space to TF conversion of A, B, C, D matrix. Now, this is going to give you the numerator and the denominator polynomial. Now, this let us view it in a more friendly manner, that is, we define the transfer function of the system for the voltage across R by the input voltage with TF, numerator polynomial, denominator polynomial of what you just obtained, and this is what you see. This is S divided by S plus 1 or S divided by S plus 1 by RC. 10,000 is RC. How does this look in the pole 0 map? Easy map sys 2. You see there is a pole here at minus 10,000, same as in the earlier transfer function, and there is one more thing, there is a 0 here at S is equal to 0, which corresponds to the numerator. The numerator, the roots of the numerator are the zeros, that is what corresponds to the 0 here. The roots of the denominator are the poles, that corresponds to the pole here. Of course, you could also see the step response also. If you just plot step sys 2, you would obtain the step response. You see here what is happening, decaying towards 0, whereas in the case of the earlier transfer function it would have been increasing. Now, let us see both together. Now, transfer functions are single input, single output systems. They can be defined only for one input, one output. The numerator is a Vi or a Vs or a Vr or any other parameter or a current, and the denominator is another variable. You cannot have multiple outputs, you have to look at them separately. But in the case of the state equation, I can have multiple inputs, multiple outputs, you can look at many outputs simultaneously. So, let us see simultaneously both the outputs. Let me go back to the notepad here and show to you. Let us take this. Let us go to the next page. Okay. Now, here if you see that, okay, let me erase some of these things. we wanted VC, and therefore, we had put this as 1 and 0, and when we wanted VR, we put this as minus 1 VC plus 1 VI. I could as well put the output equation as, that is this output equation, let us put it as VC VR equals 1 minus 1 VC plus 0 1 VI. You see, this is our Y, this is our C matrix, this is our D matrix, this is our X, this is our U. Y is equal to Cx plus du. This can be easily inputted in MATLAB, and then you could look at all the outputs simultaneously. So, let us go and make that change. So, what do we do here? You see that we see the C matrix is 1, semicolon is next row minus 1, D 0, semicolon is next row 1. So, by just modifying C and D matrices, now you are able to see multiple outputs. So, this becomes a single input multiple output system, which is very easy to define in the state equation format than the transfer function. So, let us look at what this will do. Paste, and then we have the model. Now, let us see the step response of the system. You see that both the outputs are now printed. This is output 1, which is VC. This is output 2, which is, let me go to the Windows here notes, let us take that. So, this is VC, and this is the voltage across R VR. Now, notice that there are some interesting features here. In the voltage across VR, you see that the output is growing and settles down at 1. The input is a step, a unit step. It is growing and settles down at this particular value 1 here. Now, in the case of VR, it is decaying and settles down at around 0, or exponentially it decays to 0. So, here even if there is an input, which is not 0, the output is 0, which means the gain for the transfer function is 0. So, that is what the concept of 0 explains. 0 means that at some points of the time domain curve, you will see that the output is 0 even when the input is present. That is 0 gain. And here, of course, we see that this is rising, and now when you remove the input, when you make it 0, you will see that this will decay, and when the output will exist, meaning it will not be 0 even when the input is 0, and therefore, the gain will be infinite. So, the pole, the existence of the pole and the 0. So, let us just have a bit more consolidation on this pole 0 concept. You see that we give a step. Let us we give a step like that as the input. What happened to the output? Output VC exponentially increased and then merged with the step there. So, this is value 1. What happened to the voltage across VR? It was a value which started from here and then starts going gradually down to 0. Now, let us say we close the step, that is, we bring the step back and then make it 0. So, Vi becomes 0. So, what happens to the voltage across the capacitance? So, it starts decaying like that gradually to 0. And what happens to the voltage across VR? You will see that there is a reverse current. The reason being, if you look at the circuit here, the moment the input voltage is made 0, there is a charge here. This will pump a reverse current through R and the voltage across R becomes instantaneously negative. So, that is what we are seeing, it becomes instantaneously negative, and then as the charge decays, it will decay to 0. So, this is the 0 value. So, you see here the various waveforms. This is Vi, this is Vc, and this is Vr. Look at this particular waveform combination. If you take the voltage across C or a voltage across R during this portion, that is during this portion, because during this portion of the time I know that Vi is equal to 0, because Vi has become 0. So, when Vi is equal to 0, both the cases, the VR and the Vc voltages are non-zero. Vc is not equal to 0, Vr is not equal to 0. What does this mean? This means that the input voltage is 0, output is non-zero, therefore, the gain is infinite. So, this implies the existence of a pole. How fast or how slow it decays gives you the position of the pole in the S plane. So, that is the major concept that you should understand. Now, just before that, when the input is existing, okay, so during this, that is during this portion of the time axis, here Vi is non-zero, that is Vi is not equal to 0. However, you see that Vr goes towards 0 and Vc is not going towards 0. So, it is, so therefore, the transfer function, the Vc transfer function does not have any 0 gain, it is not having any 0, whereas in the case of Vr, it goes to 0 at some of these duration, and therefore, there is a 0 gain possibility, which implies the occurrence of a 0 in the circuit and which reflects as a 0 in the pole 0 plane, which in this case occurs at S is equal to 0. So, this basically is the physical concept that would be there in any dynamical system. For example, if you look at a fan rotating, or if you look at the wheels of a vehicle rotating, you switch off the engine, which means there is no input, but the vehicle is still coasting, which is basically this region. Vi is made 0, but the vehicle speed is coasting, gradually decaying to 0, which means the output is there even though the input is 0, that is the existence of the pole, and the decay depends upon the position of the pole in the S plane. Likewise, for the zeros, if any particular variable decays to 0 like a differentiator, then there is the existence of a 0. Okay. So, this concept you should get it clear. Now, this procedure we shall use the procedure of analysis, that is obtaining the state equation, and then from there the sinusoidal steady state equation, and then from the state equation again the transfer function which can be obtained, and then taking it to MATLAB, suitably appropriately converting the state equation to the transfer function, and then doing the analysis in the three major domains, which is the time domain, the frequency domain, and the pole 0 domain, would be the standard package for, or the standard process to follow for analysis. So, let us strengthen our feel for this by doing an analysis on the RL circuit. We were seeing till now the RC circuit. Let us have a look at the RL circuit. Along similar lines, you will not have much problems. So, we have VI, R, L. Okay. Of course, this has a state variable which is I L. Now, this we take it to the Laplace domain, the circuit, by the simple process of replacing j omega in the inductive reactance with S, and then we also capitalize all the variables and they become functions of S. This is R, and then you have L, and now the reactance would be S L. Okay. And we have I L S as another variable here, and if you want to have the voltage across R, it is V R S. All in the Laplace domain, you will have the Laplace variable which is the S variable coming into the picture. So, now if you want to have a transfer function of I L as the output with respect to the input V I S, then what do you get? So, it is nothing but R 1 divided by, that is voltage, divided by these impedances, which is R by S L, plain and simple. And by small simplification, you have S 1, that is if I divide throughout by L, 1 by L divided by S plus R by L. So, we have one pole at S is equal to minus R by L. This also we saw in the last class. Now, if you want to get the voltage across R by, we will not do that. Let us take the voltage across, because we want to see a 0 across the inductance V L. So, what is V L S by V I S? Now, that is equal to S L divided by R plus S L. This is equal to S divided by S plus R by L. You see, this is 1 by time constant, just similar to the capacitor circuit 1 by RC, 1 by time constant there also. You have a 0 in the numerator, S is equal to 0, and one pole in the denominator at minus R by L. These two are similar in terms of the poles, but in terms of the zeros they are different. This is decaying in nature, this is not decaying in nature. This will settle down at some value which is whatever the input value would be. Now, if you look at the RLC circuit, now before that, where will this settle down? See, as you should see that S was representing the j omega in frequency terms. So, as the step, when we give an input step, as it starts going towards the steady state, that is omega starts tending towards 0, that is pure DC, away from the transients, this will start going towards 0, and then you will have 1 by R as the scaling in this case, that is IL by VI would be just 1 by R, or VI, whatever the input VI divided by R would be the gain. So, this is the gain, and in this case, as omega starts tending towards 0, this will also tend towards 0, and then you will see that the gain tends towards 0. Gain tends towards 0. So, that is basically the idea that you will have to get from this pole 0 analysis, the transfer function analysis. Let us do one more circuit, which is the RLC circuit, which combines both together. So, you have the R L and C. All these are combined together. Now, I will call this one as R1, L1, C1, VI, and there is VC, there is a state variable VC1, there is a current IL1 through this. So, let us quickly write the transfer the state equation. So, IL1 dIL1 by dt. Okay, you take across that one, which is L1 dIL1 by dt is the voltage across the inductor, which is VI minus IL1 R1 minus VC1. You see that this is expressed only in terms of the state equation, the state variables and the input variables, and C1 dVC1 by dt equals, we have done this in a previous session, I am just repeating this for clarity. So, the C dVC1 by dt is the current through the capacitance, which is IL1. So, putting it as the state equation form, so you have dIL1 by dt, dVC1 by dt, this is the x dot, x being the state vector. You have IL1 and VC1 as the state vector, plus an input matrix that we need to fill up VI. Now, IL1, look at the equation here, there is a minus R1 by L1 coming to the picture. Now, there is a VC1 which is minus 1 by L1 which is coming to the picture, and 1 by L1 which is coming to the picture for the B matrix, that is VI. Now, the other equation, we see that there is a 1 by C1, there is nothing here and nothing here. So, this is the dynamic equation. Output equation, what is it that you would like to see? So, let us say we would like to see Vc1. Then in that case you have 0, 1, IL1 Vc1 plus 0 into Vi. So, this is the output that you obtain. Let us have a look at the transfer function of this. Okay. So, going into the MATLAB editor, we have R1, which we will define as maybe still lesser, let us say 1 ohm, C1 is 1 microfarad, L1 equals 10 millihenry minus 3. Now, we have to define the A matrix. A matrix contains R1 by L1, that is 1, comma, minus 1 by L1, the next row, which means semicolon, 1 by C1, comma, 0. So, that is the A matrix. Then for the B matrix, we have 1 by L1, comma, then 0. Isn't it? 1 by L1, 0. Then for the C matrix, we have 0, comma 1, and for the D matrix just 0. So, this is the definition of this particular circuit. Let us copy that, go to MATLAB, clear the screen, paste, and we have the, what are the variables? A, B, C, D, R1, C1, L1. Let us have a look at the pole 0 map. Of A, B, C, D. Let us see how the transfer function pole 0 map looks in the pole 0 domain. So, you see you get a pole 0 map of the domain S plane. This is the real axis. You see that at minus 50 you have one pole, two pole. There are two poles, one pole at the positive side of the omega axis, and one pole on the negative side of the omega axis. They are exactly at the same position as far as the projection on the real axis is concerned, and they mirror each other. So, whenever you get a complex pole, you should have another mirror image complex pole on the other side of the real axis. Now, this implies that there can be some oscillation and damping which will be normal in most LC circuits, tank circuits. An LC tank circuit will give rise to oscillations because the energy gets stored once in kinetic form, then in potential form, and then keeps going back and forth. And because of the presence of the resistance, it will the energy will gradually get lost in the resistor, and that is what will cause damping, and the amplitude of the oscillation will start coming down. So, let us have a look at the step response to this particular transfer function. Step A, B, C, D. So, let us see the step waveform. As I have been telling you that for a unit step input, you see the output voltage across the capacitance, you see the oscillatory nature of the voltage here, and then gradually it damps down. You see, the amplitude is gradually decreasing. This implies the loss in the resistor, and there is a time constant involved in that one. And this damping is actually related to the position of the poles with respect to the j omega, how far it is with respect to the j omega axis. And this oscillatory nature, as we were discussing, the frequency will depend upon how far it is from the real axis, that is, what is the projection on the omega axis. Now, let us have a look at the transfer function, which we saw the pole 0 and the step response figures. So, let us define two variables n and d. N is the numerator, d is the denominator of the transfer function that we want to get. Let us use the SS to transfer function, and we want to get the transfer function of A, B, C, D, the system which is the RLC circuit. So, this results in a numerator polynomial and a denominator polynomial. Let us try to present this in a more friendly fashion. So, let us use the TF function. I will define a system LC, or shall we say RLC equals TF numerator and denominator polynomial. Now, you see here, interesting, there is a numerator polynomial with an S of order 1, which means 1 0. There is a denominator polynomial S of order 2, which means there needs to be 2 poles. Now, the roots of this is going to be, the roots of the denominator is going to be the pole locations. So, if I take the roots of D, the denominator, this will be the pole locations. You see the pole locations, that is, if you multiply by this factor, it will be 50 plus 3000 and odd in the complex. Wasn't that the same thing you got? You look at the PZ map, A, B, C, D. You see that at 50 you have 1 plus 3000 and odd and another 3000 plus something, that is at the negative omega axis. This is about the poles. Now, there is also a 0 location, which is basically the roots of the numerator. So, roots of the numerator will give you the 0, and the 0 is located at this portion. It is quite far away on the negative real axis. This can also be obtained from the state equation, that is the A matrix. A matrix contains the information of the pole on 0. Okay. Let us say you have eigenvalue of A. Eigenvalue of A gives the pole location. So, basically the roots of the denominator of the transfer function is same as the eigenvalue of the A matrix, which gives you the pole. In fact, that defines the dynamics of the system, of any system for that matter. Okay. We can get any outputs to any input, as I was saying before. going back to the notebook. Not necessary that we need to get only VC1. It could as well have been IL1. For example, if I had wanted IL1, you would say 1, 0, IL1 VC1 plus 0 VI. Or if you had wanted VR, it would be VI, the voltage across R would be the state variable IL1 passing through R1, and therefore R1 into IL1. So, if you had wanted VR, which is equal to 1, 0 IL1 VC1 plus 0 VI, but this should be multiplied by R1. That would give you IL into R1, which is VR. So, you see that you could see any variable to any variable. So, let us just modify the output equation as follows. So, the output equation would be 0 1 if you want to see VC1, it would be 1 comma 0 if you want to see IL1, and it will be R1 comma 0, it will be R1 comma 0 if you want to see VR. And in the case of the D matrix, it is 0 0 0 all throughout in this particular case. So, this is the model where we want to see the multiple outputs with respect to a single input. Let us input it in MATLAB, control paste, yes, and see the step response A, B, C, D. So, you will be seeing the step response of all three. The first one is VC, the second one is IL, the current IL, the third one is the voltage across R. In both these cases, it is decaying to 0, and in the case of VC, it is going and settling to a value which is 1. So, in this manner, we go about doing the analysis of any given circuit, whatever may be the complexity.